Hello everyone and welcome back. This is the second half of the electrochemistry lecture, which is lecture 19 in General Chemistry 2. So we're going to pick up right where I left off in the previous video, and we're going to learn about voltaic cells. So this diagram right here is what's described as a voltaic cell. This is sometimes also referred to as a galvanic cell. And these cells use chemistry to generate electricity. So what we have going on here is we have two half reactions. We have an oxidation half reaction, which occurs at the anode, and we have a reduction half reaction, which occurs at the cathode. So again, it's important to note that oxidation happens at the anode and reduction happens at the cathode. The way that I usually remember this was that the valves go together, oxidation anode, and then the consonants go together, reduction cathode. Looking a little more closely at the oxidation reaction happening here, this is zinc solid. These zinc atoms are losing electrons, so we can see that these little green spheres here, this silverish green color, these are zinc atoms. They lose 2 electrons, and we'll follow where those electrons go in just a minute. When they lose those electrons, they become ions. They become zinc 2 plus ions, and they go into solution. And so we'll have some zinc plus 2 ions floating around in solution. Where do those electrons go? We can see here that the electrons zinc is losing. The zinc atoms are losing. They are flowing through up through this piece of metal right here, what's referred to as an electrode. They flow up through the electrode, through the wires, through a voltmeter, which is able to measure the amount of voltage passing through, and they continue flowing through these wires into this electrode. And then those electrons make their way down and they will react with the copper ions in solution. So there are a bunch of copper plus 2 ions floating around in solution. They'll begin clumping up on the electrode where they will react, or they will accept the electrons that are being passed through to them from zinc, and then copper atoms are formed. And so these copper atoms will begin clumping up on one another and forming together on the copper electrode. So again, to recap, at the anodes, the atoms from the metal electrode here, zinc in this case, are oxidized, producing zinc plus 2 cations, and then the cations go into solution. The electrons travel along the wire to the other electrode on the cathode side. Here, those incoming electrons combine with the metal cations in the solution, reducing them to copper metal, which then form these copper atoms. The copper metal atoms form on the surface of the copper electrode. So what we're going to see then is, over time, the anode electrode is going to lose mass, and the cathode electrode is going to gain mass. Since here atoms are becoming ions and going into solution, the opposite process is occurring at the cathode. All right, so electrons flow from the anode to the cathode, which produces electric current. This current can be referred to as, specifically, it's being measured in terms of a voltage, and so this can be referred to as a cell potential, the electromotive force, or EMF, or cell voltage. You're going to hear me refer to it most commonly as cell potential. Now, a few other things to note. As zinc is oxidized in the anode, we do have a large buildup of zinc plus 2 ions in the solution. And then as copper is reduced in the cathode, we're going to have some excess nitrate ions remaining in solution. And so we need to deal with this. Eventually, if left to its own devices, too much charge will build up. Too much positive charge is going to build up in this solution. Too much negative charge is going to build up in this solution. And this is what the salt bridge is for. The salt bridge allows for migration of cations and anions between the two solutions. This allows a neutral charge to be maintained. So this is the importance of the salt bridge right here. Electrons do not flow across the salt bridge. Cations and anions flow across the salt bridge to maintain charge on both sides. All right, you're also going to see something referred to as line notation. Line notation is a shorthand way of representing a voltaic cell. And the way line notation is written is you write it exactly as it appears in the diagram. So you start by writing the anode, so you write the solid of the anode, the ions of the anode. Here, the single letter represents a phase boundary between the solid and the aqueous solution. Then you have the double line right here, which represents the salt bridge separating the two cells from one another. Then we have the solution in the cathode, the copper 2 plus solution, and we have the solid of the cathode, the CuS, and then again a single line separating these two phases. So this is how we represent voltaic cells using line notation. All right, next let's describe how we can calculate the cell potential. Again, this can be referred to as the electromotive force or a cell voltage. This is the amount of voltage we can expect the cell to generate. So standard cell potential is represented by this simple formula. E cell equals E cathode plus E anode. This little degree symbol right here is referred to as a knot, and it stands for standard. So this is the standard potential, the standard cell potential is equal to the standard reduction potential plus the standard oxidation potential. And I do also want to note that an oxidation potential is just the negative of the reduction potential. So these two values have the same magnitude. Their signs are just flipped since reduction and oxidation are just the reversed processes. So you may also see the formula E cell equals E cathode minus E anode. I'm going to use this formula for the rest of my slides, but this is very common as well. So these potentials right here, these are measured for various reduction half reactions. They're compared to a reference value and then tabulated as E values, and we can look them up in a table. These tables often look something like this, where E naught there is for the reaction as written, and these are all reduction half reactions. Notice they all show electrons on the left side. So this is a reduction potential table. So the more positive values here indicate a more favorable reduction process. So fluoride, for example, F2 plus 2E minus to form two fluoride ions. This has a reduction potential of plus 2.866. So a positive value here actually means that this cell will produce voltage. It will produce voltage. This is a favorable reduction process. So the further up this table you are, the more favorable the reduction process is, which makes these species good oxidizing agents because they are very good at taking electrons, especially the ones above 0. If we reverse the reactions listed in the table, we get an oxidation half reaction, but the sign would change as well. So what that means then is the values towards the bottom here, the ones that have very negative reduction potentials, are going to have very positive oxidation potentials, meaning that they have a favorable oxidation process. I do want to note here that changing the coefficients of a half cell reaction does not change the value of E. So let's do some redox predictions using a table. Excuse me. We're just going to go over A and B right now, and then we'll come back to C and D a little bit later. So letter A, which would be the best oxidizing agent? Br2, CO2+, or Ti2+? So look at these three half reactions right here. Br2, CO2+, and Ti2+. So here we show that Br2 is accepting 2 electrons and forming 2 Br-. So remember, for something to be a good oxidizing agent, it needs to be good at getting reduced. So Br2 is being reduced here with a reduction potential of positive 1.087. When the cobalt and titanium ions are being reduced, they have negative reduction potentials, which indicates an unfavorable process. So the answer to letter A is Br2. It has the most positive reduction potential, meaning it has the most favorable reduction process and is therefore the best oxidizing agent. Then going back to letter B, which would be the best reducing agent. So if I look at Br- here, CO here, and Ti here, so which would be the best reducing agent? Basically that question is asking which one would have the most favorable oxidation process. So here we're looking at these 3 different species in the reactants, so we're reversing the reaction. We're going from Br- back this way, from CO back this way, from Ti back this way. So we should flip the values here, or we should flip the sign on these values. So Br minus would have an oxidation potential of negative 1.087. Cobalt would have an oxidation potential of plus 0.280. Titanium would have an oxidation potential of plus 1.630. So titanium has the most favorable oxidation process, meaning that it would be the best reducing agent. And again, that logic is explained in a little more detail here. All right, next we're going to look at calculating standard cell potential, again also known as electromotive force or cell voltage. So suppose you were given this voltaic or galvanic cell, so you're just given the cell in line notation, remembering that the anode is written first and the cathode is written second. So here's our anode and here's our cathode. Remembering that our formula here, our standard cell potential, is E cell equals the reduction potential of the cathode plus the oxidation potential of the anode. You'd want to start by writing out the half reactions. So our anode half reaction, where oxidation is occurring, is zinc loses electrons to form zinc 2 plus and 2 electrons. And then our cathode half reaction, where the reduction occurs, is copper gains 2 electrons to form, or the copper 2 plus gains 2 electrons to form solid neutral copper. Now what you would do in this problem is you'd likely be provided some sort of table. So you would look up these two half reactions in the table and you would find their reduction potentials. Copper has a reduction potential of plus 0.342. Zinc has a reduction potential of negative 0.762. And then there's just one more thing to do. Remember that standard cell potential, E cell, is equal to the reduction potential of the cathode plus the oxidation potential of the anode. So this value can just be plugged in as is. This is a reduction potential. But this value right here, again, this is a reduction potential, but the reaction that's occurring at the anode is oxidation, and we want the oxidation potential. So we're going to take this value right here, and we're going to flip the sign. So E cell is equal to 0.342 plus positive 0.762, giving a final answer of 1.104 volts. All right, next let's look at this question. What is the standard cell potential of a voltaic cell made of a cadmium electrode in a 1 molar cadmium 2 plus solution and a Cr electrode in a 1 molar Cr3 plus solution? I would actually encourage you to try and pause the video and answer this question on your own. So pause the video, write this prompt down, and then if you go back earlier in the slides to the slide where I showed earlier in the slides or earlier in the video to where I showed the reduction potential, both of these half reactions are in that reduction potential I showed a few slides ago. So you should be able to come up with the answer for this problem. So again, go ahead and pause the video and give this one a try. All right, let me walk you through the steps. So start by writing out the two reduction half reactions and their E values. So we've got Cd2 plus 2E minus forms Cd. This is the cadmium half reaction. It's got a reduction potential of negative 0.403 volts. And then chromium, Cr3 plus 3 electrons form Cr. It has a reduction potential of negative 0.744 volts. Now, you may have noticed in this problem that we aren't told which is the cathode and which is the anode. However, we should note that the more negative reduction potential would rather be oxidized. So from this, we can infer then that cadmium, that is going to be our reduction half reaction, and then chromium, that will take place at the anode. That'll be our anode or oxidation half reaction. So here's that half reaction written with the cell potential of negative 0.403 volts. Then the chromium half reaction, we're flipping it, so we should also flip this value to give us an oxidation potential of plus 0.744 volts. Then we can use that equation I described earlier, so negative 0.403 plus 0.744 gives a final answer of 0.341 volts. Let's go back to questions C and D to analyze, or let's use what we just learned to go back and analyze questions C and D. So what we're going to do here is we're going to calculate the standard cell potential of the reaction as written, And from this, we can determine whether the reaction will proceed in the direction shown. If the reaction has a positive voltage for each cell, the reaction will proceed spontaneously as written. It's considered to be a galvanic cell that will produce electricity. If you have a negative voltage, this means the reaction will not proceed as written. You would need to input electricity to get that reaction to proceed, and that's called an electrolytic cell, which we'll see at the end of this lecture. So first question, is Br2 capable of oxidizing CO? Let's write the half reactions. So the half reactions going on here are Br2 plus 2E minus forms 2Br minus. The other half reaction is CO, forms CO2 plus, and gives off 2 electrons. So that first half reaction has a potential of plus 1.087. That second half reaction, again, we flipped this half reaction, so we should flip the sign to get an oxidation potential of positive 0.280 volts. And when we add those two values together, we get a cell potential of positive 1.367 volts. So again, a positive voltage means the reaction will proceed as written. We can say that it is spontaneous. Therefore, Br2 is capable of oxidizing cobalt. Letter D, is cobalt capable of reducing titanium 2 plus? Let's again write out those half reactions as written. So Ti2 plus 2E minus forms Ti, and CO forms CO2 plus 2E minus. We can see that the titanium half reaction is unchanged from what's in the table, so we have a reduction potential of negative 1.630 volts. The cobalt half reaction is again being flipped relative to what's in the table, so this is an oxidation half reaction, so I should flip the value there, giving me an oxidation potential of plus 0.280 volts. When I add these values together, the reduction potential for the cathode and the oxidation potential for the anode, I get a value of negative 1.350 volts, meaning then that this reaction will not proceed as written. It is non-spontaneous. All right, here's a question that I would like you to try. So I would encourage you to pause the video and maybe just write out a simple diagram on the notebook paper you're following along with, and see if you can label the parts of the voltaic cell diagram using the line notation and using this general diagram. So answer questions A through E by labeling this diagram. Then I would like you to again go back to that table with the reduction potential values, and calculate the voltage for this cell. So again, please pause the video and give these questions a try. All right, so labeling these things, the cathode is over here, the anode is on this side. This is the metal being used for the anode, so this would be the aluminum right here. This is the metal being used for the cathode, the electrode, so this is the nickel right here. The ions in each solution, we would have aluminum ions here and nickel ions here. Here's our salt bridge, and when you went to calculate the cell potential here, you should have gotten a value of around 1.405 volts. All right, I've got one more practice problem for you to try. So go ahead and pause the video so you can come up with the answer for these 4 questions. All right, and the answer is here. The oxidation half reaction, this would be what's occurring at the anode, so that would be Ag forming Ag plus and giving off 1 electron. The reduction half reaction would be Au3 plus 3 electrons to form Au. The balanced overall reaction should have coefficients of 3 in front of the silver ions to balance out the electrons. And then letter D here, there should be 3 moles of electrons being transferred in the reaction. All right, I've got another question for you to try. You've been tasked with designing a voltaic cell that can produce around 1.50 volts. Use the table of standard reduction potentials to propose a redox pairing for this design. So what you need to do then is pick 2 half reactions that will result in a value of E cell equals 1.5 volts. So sketch a diagram of your voltaic cell design, label the anode and the cathode, write the line notation, then calculate the voltage and balance the overall cell equation. A couple hints I want to give here. Again, remember that the formula for cell potential is E cell equals E cathode minus E anode if you're just keeping it in reduction potentials. So what you want to do then is set E cell equal to 1.5 and to rearrange, and you should find then that E cathode should be, or anode should be equal to E cathode minus 1.5. So an easy way to do this type of problem is to go down the table of reduction potentials, consider each one as a possible cathode, subtract 1.5 from its value to see what anode potential would need to be, then see if you can find another value in that list that is close. If not, you can cross off that cathode. So I don't have the answers written out here because there are multiple possible different answers. I would just encourage you to try this as a useful exercise to make sure that you're comfortable with cell notation. But we're going to keep it moving, and we're going to move on to a slightly different topic, but still related. This is called electrical work. So voltaic cells, because they produce electricity, they can be used to do electrical work, which equals the total charge times the voltage. So electrical work, again, is equal to total charge times the voltage of that cell. The charge on 1 mole of electrons is given by a constant referred to as Faraday's constant, and this is 96,485 coulombs per mole. So the capital C there is coulombs. This is a unit of charge. So this is how much charge 1 mole of electrons has. I do also want to note that coulomb can be broken down as into joules over volts. So the total charge is the number of moles of electrons N transferred in the balanced redox reaction multiplied by Faraday's constant. So again, total charge is moles of electrons transferred times Faraday's constant. So effectively N times F. So then we can say then that electrical work is equal to N times F times the cell potential of the cell. Couple more notes here I want to talk about. Non-standard conditions. The values in the standard reduction table we looked at are measured under standard conditions. That's what that little degree symbol means. Standard conditions means concentrations of 1 molar and a temperature of 298 Kelvin. But as a voltaic cell produces current, the concentration of the ions in the solution will change, which means the voltage will change. So we can use an equation called the Nernst equation. This allows us to calculate the voltage of an electrochemical cell where the temperature and or concentrations may be different than the conditions used for measuring standard reduction potential. This equation is E cell. Notice the lack of a degree symbol here. So this is the cell potential of that cell under any conditions. These are equal to the standard cell potential minus RT over NF times ln of Q. So R is the ideal gas constant, T is the temperature, N is the moles of electrons, F is Faraday's constant, and then Q is the reaction quotient. If the temperature is at 298 Kelvin, so you will see this version of the equation, at least for my course, you'll see this version of the equation given on the reference sheet. But if the temperature is 298 Kelvin, this can actually be simplified. So if we plug in 8.314 as our ideal gas constant, 298 Kelvin as the temperature, and 96,485 as Faraday's constant, we get the simplified version of E cell equals E naught cell minus 0.0257 volts over N times ln of Q. And so again here, N here is moles of electrons transferred. So walking you through a practice problem, what is the cell potential for the following reaction at 25 degrees Celsius? All right. So let me walk you through the steps. Notice that we're at 25 degrees Celsius, which is 298 Kelvin. So we can use that simplified version of the equation. So I'm going to start by writing out my half reactions. My oxidation half reaction is aluminum forming aluminum 3 plus ions and giving off 3 electrons. My anode half reaction, my cathode half reaction, the reduction, is 2 electrons plus copper 2 plus to form copper. We need to make sure the number of electrons balances, so I'm going to multiply the oxidation half reaction by 2 and the reduction half reaction by 3, giving me an overall reaction of 2Al plus 3Cu2 plus forms 2Al3 plus and 3Cu. We note then that 6 moles of electrons are being transferred, so N equals 6 here. So we want to calculate E cell, or E naught cell, so we need to calculate the standard reduction potential. So the reduction potential for the cathode is 0.342. The oxidation potential for the anode, 1.662, giving me an E naught cell value, a standard cell potential of plus 2.004 volts. Then we can set up our Q value. Our Q value, remember Q, reaction quotient, is calculated the same way as the equilibrium constant. So it's products over reactants. So Al3 plus squared over Cu2 plus cubed. Note that the copper here and the aluminum here are included because they're solids. So you can plug in the concentrations you're given. 0.2 or 0.15 molar for the aluminum, that goes in on top. 0.025 molar for the copper, that goes on the bottom. This gives me a Q value of around 1440. And now I can finally plug all these values into this equation. So plus 2.004 volts goes in here, 6 moles of electrons goes in here, and 1440, the Q value, goes in right here. And this gives me an E cell value of plus 1.973 volts. So this is how we can calculate non-standard cell potentials using the Nernst equation. The majority of the time, these questions will be at 25 degrees Celsius, and so you can use the simplified version of the equation, but if it's at a different temperature, you would want to use this version of the equation here, plugging in whatever your T value is in Kelvin, 8.314 for R, and 96,485 joules over volt mole for F. All right, next let's analyze the relationship to equilibrium. So eventually, the voltaic cell will reach a point where the battery dies. The redox reaction has come to equilibrium, and the cell potential is 0. When equilibrium is reached, the reaction quotient Q equals the equilibrium constant K for the reaction. If we take the Nernst equation and we let Q equal K and E cell equals 0, we get this relationship. And so this equation right here is how we can relate the standard cell potential to the equilibrium of a reaction. E naught cell equals RT over NF ln K. So again, I want to emphasize then when a battery dies, that means it's reached equilibrium, it's no longer producing voltage. So that's why we can say E cell equal to 0. And again, remember, if you're at equilibrium, Q equals K. So that's the substitution we made to the Nernst equation to give us this equation right here. Let's take a look at how we would use that equation. What is the equilibrium constant for the following reaction at 25 degrees Celsius in the forward direction? So write out your two half reactions. Our oxidation half reaction is silver giving off 2 electrons to form 2 silver ions. Our reduction half reaction is the iron 2 plus accepting 2 electrons to form solid iron. So here our N value is 2. Now we can calculate E cell. So you'd look up these values in a table. You'd find that the reduction potential for iron is negative 0.447 volts. You would also find that the reduction potential for silver is actually positive 0.80 volts, but since silver is being oxidized here, you actually need to flip that, and silver has a negative oxidation potential of negative 0.800 volts, and so we get a value, an E naught cell value, a standard cell potential of negative 1.247 volts. Now we can use this equation, E naught cell equals 0.0257 volts over N times ln of K. Now we're trying to solve for K here, so if I take this equation and I rearrange to solve it for K, I should find that K is equal to E, so lowercase e, the constant E, to the power of E cell times N divided by 0.0257 volts. I can plug my values in, so negative 1.247 volts times the N value of 2 divided by 0.0257 volts. And we get a K value of 7.16 times 10 to the negative 43rd, an incredibly small K value. What this negative E value here and this very small K value tells you that the reaction is not spontaneous in the forward direction. It's going to strongly favor going in the reverse direction. All right, and our last topic on electrolytic cells. Thus far, we have studied voltaic cells or galvanic cells, which convert chemical energy into electrical energy. An electrolytic cell reverses this process. It converts electrical energy into chemical energy in a process that is known as electrolysis. A good example of this is the electrolysis of water, where water can be split into hydrogen and oxygen gas, a reaction that is commonly theorized for using to produce rocket fuel, where ice could be put through this process and separated into hydrogen and oxygen gas. So if you look at these two half reactions and their potentials, you see that the overall reaction has a cell potential of negative 1.229 volts, meaning that this reaction, it's not a galvanic cell. It will not produce electricity. Rather, electricity needs to be added to this reaction to get it to move forward. So again, the negative sign here means electricity is required, not produced. So the E values work a little bit differently than some of the thermodynamic quantities like enthalpy, like delta H that you've worked with before. It's opposite. A positive sign means electricity is produced. A negative sign means electricity is required. So electrolytic cells are often used in electroplating, in which a thin layer of one metal from ions in solution is applied onto another metal, the cathode. We can determine the mass of metal which was deposited if we know the stoichiometry of the reaction and how many electrons are transferred. We can then determine the number of electrons transferred if we know the total electrical charge used during the process. So as seen in previous slides, the total charge is equal to the moles of electrons transferred times Faraday's constant, or NF. One other thing we want to note is that total charge can be determined based on current and the length of time. So current, which is often represented with the variable I, is usually in units of amperes or amps, the capital letter A. I'm sure you've heard of amps before. And the unit amp is actually just 1 coulomb per second. So 1 amp is equal to 1 coulomb per second. So combining this with what we had from the previous slide, where total charge is equal to current times time, and we also said that total charge is equal to N times F. So if total charge is equal to current times time, so current I and time T. Also, if total charge is equal to moles of electrons times F, we can say then that I times T, current times time, is equal to N times F. And putting this all together, we can solve for the moles of electrons by taking the current I times the time T in seconds divided by Faraday's constant F. Let's look at how this question would be used in practice. So in a process used for electroplating copper, a current of 10.23 amps was passed through an electrolytic cell containing aqueous copper sulfate for exactly 1 hour. First, how many moles of electrons passed through the cell? So the equation we just established was moles of electrons N is equal to the current I times the time T in seconds divided by Faraday's constant F. So the current here is 10.23 amps, which is the same thing as 10.23 coulombs per second. The time T should be in seconds, so 1 hour is 3,600 seconds. And then Faraday's constant F is 96,485 coulombs per mole. If you follow along with the units, coulombs cancels with coulombs, seconds cancels with seconds, moles flips up to the top. So 10.23 times 3,600 divided by 96485 gives an answer of 0.3817 moles electrons. So this is the answer to letter A. Letter B, what mass of copper was deposited at the cathode? Here, what you can do is, this is basically just a stoichiometry problem. So from the problem, the solution contains copper sulfate, so it contains copper plus 2 ions. The reduction at the cathode, therefore, must be copper 2 plus 2 electrons forms solid copper. This reaction involves 2 moles of electrons for each mole of copper. So to find the mass of copper, we can just use some stoichiometry using our answer from part A. So I'll take 0.3817 moles electrons. I'll convert from moles electrons to moles copper using the ratio in the equation here, where 2 moles of electrons produces 1 mole of copper. And then now that I'm in units of moles of copper, I can find the mass of copper using its molar mass. So 0.3817 moles electrons times 1 mole copper over 2 moles electrons times 63.55 grams copper over 1 mole. So C, moles of electrons cancels, moles copper cancels, and you would get a final answer of 12.13 grams copper. So on these electroplating type problems, use the current you're given, the time, and Faraday's constant to find moles of electrons, and then simply use stoichiometry to find the mass of the metal being produced. All right, that concludes this lecture. That's the end of part 2 of electrochemistry. I've got 3 additional practice problems for you to try, so I would recommend that you pause the video and go ahead and give these 3 problems a try. And then the answers are right here. That concludes this video. That concludes lecture number 19. As always, I hope you found this useful. If you've got any questions, please feel free to reach out to me via email or leave a comment down below, and I will help as best as I can. That's all for now. I hope you have a great day, and I'll see you in the next one.